So in this video, what I would like you to do is to calculate this definite integral, and then after you have had a go with pen and paper, if you come back, I'll provide a detailed solution. I'll actually provide two very slightly different solutions and give you some comments about this integral and other related integrals. So I will see you after you've had a go at it. Okay, welcome back. Let's look at the answer. So on this slide, I'm going to calculate this definite integral, and I think this is an integral that you should be trying to do by inspection. If you look at the numerator here, the numerator is essentially the derivative of the denominator. So therefore, you can expect to get a logarithm. And the argument of the logarithm is going to be the modulus of the denominator. And of course, there could be factors, numbers, minus signs. So let's just leave a bit of space here, and we can work out what they are by differentiating this. So if you differentiate the log of the modulus of a function, you get 1 over the function, which is this, multiplied by the derivative of that function, and the derivative of that function is going to be minus e to the x, because the derivative of e to the x is e to the x. But here we've got plus e to the x, so that means we just need to put a minus sign here, and that will mop up the minus sign you get when you differentiate the argument. So the derivative of this is this. So now we put the limits in. At the upper limit, we have x is 2, so we have minus the log of 1 minus e squared. And then we subtract and evaluate the whole thing at the lower limit. We've got multiple minus signs, so after this minus sign we open a big bracket, and then we put this down and evaluate it at the lower limit. So it's minus the logarithm of 1 minus e to the 1, which is just e. So we can now expand these brackets. Minus minus is plus. So I'm going to write the positive term first, and then this term I'm going to write second, minus log of 1 minus e squared. We can now combine them using the rules for logarithms. The log of a minus the log of b is the log of a over b. So it's the log of 1 minus e over 1 minus e squared. 1 minus e squared is one of our favourite algebraic things. It's 1 minus e times 1 plus e. The 1 minus e's will cancel, and we're going to get the log of 1 over 1 plus e. So that's the log of 1 plus e all to the minus 1. We can take that power outside. So what we see is that our integral is negative because the log of 1 plus e is positive. Log of 1 is 0. Anything greater than 1, you get a positive result. So the integral is negative. And that is what we would expect, because if we look at our integrand, over our range of integration, starting at x is 1, we have 1 minus e, so that's negative because e is greater than 1. And then it goes up to 1 minus e squared, and e squared is also, of course, greater than 1, so this is negative. So as the integrand is negative. So this is correct. Everything I've written here is, I think, correct, but there are too many minus signs. And what I want to do is I want to use this example on the next slide, do it in a very slightly different way, and then after that talk about why, when we integrate such functions, we have the log of a modulus. So I'm going to talk about that in 2 slides' time. But let's first just do this integral in a very slightly different way. So here is our integral again, and what I want to do is I want to just rewrite it ever so slightly. And this is based on the fact that there is this minus sign here and our denominator is going to be negative over the range of integration. So what I'm going to do is I'm just going to rewrite this ever so slightly by saying I'm going to put a minus sign in front of the integral, and then on the denominator I'm going to have a minus sign in front of the denominator. So all I've done is I've multiplied and divided by -1. So I haven't changed anything. This is an identity. These two results are the same. So we can just rewrite this now as minus the integral from 1 to 2 e to the x, and in the denominator we have -1 plus e to the x, and I'll just write the positive term first. So that's e to the x minus 1 with respect to x. And now we see immediately that if we do the integral, we are going to get, in the same way as on the previous slide, the log of e to the x minus 1, and I've got a minus sign outside from here that we had from our little bit of algebra. And if we differentiate this, we're going to get 1 over e to the x minus 1 times the derivative of the argument, which is e to the x. So there's no need for an extra minus sign there. And this is evaluated between x is 1 and x is 2. And now if you just carry on, we have minus, open big brackets, log of e squared minus 1 minus log of e minus 1, close brackets. And now we have minus, and this is from the rules for logs, the log of e squared minus 1 over e minus 1. And using the cancellation as before, we know that e squared minus 1 is e plus 1 times e minus 1. So the e minus 1 factors cancel, and therefore we obtain that our integral is minus, because that's outside, and then it's the logarithm of mod e plus 1, and e plus 1 is positive, so we don't really need the modulus. And that is our answer for the integral, and it's exactly the same answer that we obtained on the previous slide, but there are fewer minus signs. Now, I think this idea of looking at this and thinking this is negative and just saying, well, why don't I multiply top and bottom by a minus sign and take one of these minus signs outside, is something that can be helpful to people. So, for example, supposing, I'm just going to put in a few examples here, you wanted to integrate 1 over 1 minus t with respect to t. You can write that as minus the integral 1 over t minus 1 with respect to t. And based on my experience, I think people on average are then going to make fewer minus sign errors integrating that than they would if they integrated that. Or similarly, if you wanted to, you could be trying to integrate something like the integral of 1 over 1 minus t cubed, say. And again, that's with respect to t. And again, that is minus, because this is an odd power in the bottom, 1 over t minus 1 cubed with respect to t. So I think this sort of small algebraic alteration, or just multiplication top and bottom by a minus sign, can sometimes be helpful to us. But what I'd like to do now in the rest of this video is I'd like to talk a little bit more about the role of the modulus in such integrals. So let's go on to another slide to look at that. So the example I want to look at here is the integral of 1 over x minus 1 with respect to x. And that gives us the logarithm of x minus 1 plus an integration constant. But if I multiply x minus 1 by a minus sign, its modulus is unchanged. So this is exactly the same as the logarithm of the modulus of 1 minus x plus a constant. And you can see very easily that both versions have the same derivative. So if I take this and I differentiate it, the derivative of the logarithm of the modulus of a function is 1 over the function multiplied by the derivative of that function. So this function and this function have to be exactly the same. And the derivative of this is 1. So therefore we get 1 over x minus 1 times 1, and that is 1 over x minus 1. If we had written it this way, then we see its derivative is 1 over the argument of the modulus, so 1 over 1 minus x, times the derivative of this same argument, 1 minus x. That derivative is now minus 1, so we get minus 1 times 1 over 1 minus x. So that's minus 1 over 1 minus x. And if we multiply top and bottom by a minus sign, this becomes plus, and this becomes minus 1 plus x. So we get overall 1 over x minus 1. So that's exactly the same. And the message I hope it's sending to you is that writing it this way is probably a bit easier to integrate and to differentiate than writing it this way. So finally, on the next slide, I want to look at why we have the modulus in the first place. So on this slide, I just want to argue why we have the modulus in these integrals. So if you go back to the beginning of calculus from first principles, and I have a video on that in the playlist about calculus from first principles from definitions, you can show from the definition of e, the base of the natural logarithm, that the derivative of the natural logarithm of x, so in other words, the derivative of the logarithm to the base e of x is 1 over x. And in this derivation, it is assumed that x is greater than 0. So that's the result we start with. Then, from the fundamental theorem of calculus, it follows that the integral of this will be the natural logarithm. So the integral of 1 over x with respect to x is the natural logarithm of x plus some integration constant. But here we are assuming that x is greater than 0. I'm giving this equation a name. I'm calling it star. So what about the case where x is less than 0? Now, I'm not going to write the logarithm of a negative number because that leaves the real world and we have complex variables, but I'm going to look at the integration. So if we're integrating 1 over x and we know that x is negative, what we can do is multiply top and bottom by a minus sign. So we have minus 1 over minus x. And if x is negative, minus x is positive. Now, there is a generalization of this formula, which I'm assuming you know, which is that the integral of the derivative of a function divided by a function with respect to x is the logarithm of that function. But here I'm assuming that the function is itself positive. Now, here we have exactly this situation. If x is negative, minus x is a function of x and it's positive. And minus 1 is the derivative of that function. So I can therefore use this result and say the integral of 1 over x with respect to x, if x is negative, is going to be the logarithm of this positive function minus x plus some integration constant. This is the case when x is negative, and I'm giving this equation a name. I'm calling it dagger. So combining this equation star and this equation dagger together and using our piecewise definition of the modulus function as x when x is greater than naught and minus x when x is less than naught, then we get that 1 over x integrated with respect to x is going to be the logarithm of the modulus of x plus c. Because if x is positive, the modulus of x is x. That is that equation. If x is negative, the modulus of x is minus x. And that is this equation. And of course, this is not defined for when x is naught. So I'm just going to say if x is not 0. And generally speaking, if our function here in this equation could be positive or negative, we would need to put modulus signs here. So that concludes our argument for why we put the modulus sign around the function when we integrate. And what we've seen on the previous slides is how it works when we differentiate.